introduction. Now, welcome to the last part, to my third lecture. And as already announced, it will be on ultra-long-range molecules. And I also would like to thank Frederick. He has picked up several items which I'm going to be using, including the von Oppenheimer approximation, and particularly also the classification of Rydberg molecules, what different types of Rydberg molecules you can have. And I will be addressing this specific one, which you usually call ultra-long-range molecules. Now, that you have seen, this is back in Hamburg, the place I come from, the Center for Optical Quantum Technologies. Now, let me give you a brief outline of the contents. I will give you quite a lengthy motivation and introduction, then coming to what is two important classes, so-called trilobites and butterflies, which are specific features of the ultra-long-range molecules. Then some facts about recent developments, experimental and theoretical. This is just a short description. And then this is the main part. I will describe to you how ultra-long-range molecules do behave if you have an external electric field. I will describe to you some exotic species, linking back to the previous lecture of how you can create giant dipole molecules. Now, I have been talking extensively about giant dipole atoms. Now, use these kinds of in-standard atoms to create giant dipole molecules, which are in the spirit of the trilobite-type binding mechanisms in these huge molecular systems. Now, let's come back and let's start with what types of molecules do we know. Well, what you know from your lectures is one type of binding is certainly covalent binding. That means different atoms share electrons. I will come back to that in a minute. Another type of binding is ionic binding. That means the two species in a diatomic molecule have different electronegativity. Like, for example, in lithium chloride, the lithium can give an electron, the chloride wants to accept an electron, and therefore you get an ionic binding mechanism. These two are major bonding mechanisms which we know do exist in nature. An important additional effect is electron correlations, which plays an important role in binding. Now, let me work out this a little bit more, the theory behind this. This usual binding as we know it. Well, what we have is the Schrödinger equation. The Schrödinger equation I write down here for the total system. That includes electrons and nuclei. What we do, and that has been nicely described by Frederick, we do a von Oppenheimer approximation in molecular physics. Yeah? And the von Oppenheimer approximation is based on the fact that you separate the electronic and the nuclear motion. And you do that on basis of the fact that you have a fast electronic motion and a slow nuclear motion. And then you define a Hamiltonian, which is He, an electronic Hamiltonian, which consists of the kinetic energy of the electrons plus the interaction of the electrons with each other plus the interaction of the electrons with the nuclei. And of course there's also the interaction of the nuclei among each other, but this is a constant for the electronic Schrödinger equation, which is defined as He psi E is equal to the electronic energy, it's called E psi E. Now, the psi E is the electronic wave function for fixed nuclei. It depends on the electronic coordinates and parametrically on all the positions of the nuclei. And the E is a function of these nuclear positions. It's a potential surface, it's an adiabatic potential energy surface. So I call it adiabatic PES, potential energy surface. So now, usually if you try to calculate the electronic structure, this means you're going to solve this Schrödinger equation. This is fixed positions of the nuclei. You try to solve the electronic Schrödinger equation and try to get the eigenfunctions, the electronic eigenfunctions, and the eigenvalues, which are these adiabatic potential energy surfaces. Now that is a complex story, because usually you have dozens, you have hundreds, you have thousands of electrons, increasing the size of the molecular system and the nuclear charge number of the atoms involved in the molecular system. Now, but that all goes back, calculating electronic structure goes back to what you might call quantum chemistry. It's nothing to do with cooking, it's nothing to do with synthesizing any molecule, it has to do with the theory of electronic structure. So quantum chemistry is many-body physics of molecular systems. And how do you do that? You solve this equation. Usually what you start with, most of the methods, most of the electronic structure methods, they start out with doing something what you call in physics a mean field. That is, in this case of identical fermions of electrons, this is a Hartree-Fock approach. Okay? And this Hartree-Fock approach takes one Slater determinant, so a single Slater determinant, and it variationally optimizes the orbitals which are in this Slater determinant. So it is based on a variational principle. And that gives you the Hartree-Fock wave function. Now, that is, as I say, the mean field. That is without correlations. Without correlations, it turns out that physics is usually not well described, and binding of molecules is not well described. It's very crude. For some things it's qualitatively correct, but for many other things it's really incorrect. So you need to account for correlations. And how do you account for correlations? This is, you take the Hartree-Fock approach, you take the single orbitals, the single particle orbitals which come out from Hartree-Fock, and you do a multi-configurational approach. So you superimpose many of these Slater determinants. So you have many, and this could mean thousands, this could mean millions, many Slater determinants superimposed. Superimposed means here linear combination of them. You make an ansatz of a linear combination of these Slater determinants. Now, quantum chemistry is, in a sense, has developed over the past 80, 90 years here, dozens, if not hundreds of methods based on more or less this line. There are many other methods like coupled cluster approaches, green function approaches, but essentially they superimpose all these different Slater determinants which come out from Hartree-Fock in one or another way, in a sophisticated way, and then you can finally get the electronic structure of the system and can make predictions on the eigenstates and on the eigenenergies. And then you can tell whether there is binding or whether there is not binding. Now, one issue which is important to note here is technically, since this is a many-electron problem, you need to describe this many-electron wave function. Technically, most of these methods are based on what people call GTOs, which is Gaussian-type orbitals. Now that sounds a little strange maybe, because what do Gaussians have to do with the electronic structure? Well, if you take the hydrogen function, this is a Slater function, e to the minus r, an exponential simply. Why do we use Gaussian-type orbitals? Well, you do it because Gaussians are extremely convenient to do practical calculations. All the numerics which you need to do, which is extensive numerics, large-scale computations, all the numerics is easily done, and all the matrix elements which you have to compute of the Hamiltonian is easily done with these Gaussian orbitals. That's why you use them. Now, why do I tell you this story? Well, first of all, it refers to how you do molecular structure calculations, how you compute electronic structure for molecules. And second, I want to tell you, now you do that for the ground state, you do it for the first excited state, you do it for the second, third, fourth excited state. But these methods inherently have limitations if you try to go to higher excitations. In particular, if you try to go to Rydberg molecules. So quantum chemistry is a powerful area, but it has its problems if you go to Rydberg electronic structure. Rydberg electronic structure here is typically, as Frederick has pointed out, one of these classes of Rydberg molecules. You take an electron from a core, from a tightly bound molecule, you excite it to a highly excited state. And that is an electron circling around an H2 plus core, in this case of an original H2 molecule in its ground. Then such a highly excited state could not be described by quantum chemistry. You need to refer to other methods. And the ultra-long-range molecules are a specific class of systems that cannot be approached by standard quantum chemistry methods yet. So, and this class I'm going to be addressing here is not this one. See, a H2 plus core and an electron. It is an extreme other case where you bring a neutral atom into a cloud of Rydberg atom. That means you have an extended Rydberg atom, you put in what you call a neutral perturber, a neutral ground state atom. Here, in this case, you have these tightly bound two atoms, and then the electron outside. In this case, I'm referring here to, which is sketched here, is you have extended electronic atomic wave function, and then you bring in a perturber into that system. And as you shall see, this is a setup which yields under certain conditions bound states. But now, the distance between the two atoms, the cores, is huge, as opposed, in contrast to this, where this is angstrom, this distance will be thousands of angstrom. So this is what you call ultra-long-range molecules. The two nuclei are very much apart. And so the system is composed of an atomic ion, of a neutral, and a widely dispersed electronic cloud. And this goes back originally to the work of Chris Green, Dickinson, and Hossein, who is the organizer over here, in 2000. And what they found is, I give you a few facts of these systems. What they found is, of course, that the size of these objects scales with n squared, that we know already from the normal Rydberg atoms. But one main feature is something which you would barely get over here. Now let me go back to that point. Here, if you do an electronic structure calculation and you calculate this energy over here for a diatomic molecule, typically what you get is energy as a function of the internuclear distance. You get this type of behavior here. This is the elevated potential energy curve in this case. This is the distance r, this is the energy. This is what you all know, and the vibration states are in here, and this is the dissociation threshold, and this is the repulsive inner part. And you get an equilibrium somewhere here. But typically this is a curve which has one minimum. This is quite universal. If you go up in excitations in molecular cases, you might get, in rare cases, two wells, but typically you have one such well, particularly in the ground state. Now, these ultra-long-range molecules have an oscillatory behavior, as you shall see in a minute. So that's not only just these type of curves, but this kind of oscillatory behavior. So that's already quite weird, yeah? And in these individual minima, which are then out there, you have vibrational states that can be localized, that can be delocalized, and these new equilibria occur typically at very large distances, 3/2 n squared, n being the principal quantum number. Then you have these vibrational bound states out there in the gigahertz or the megahertz regime. So let me for completeness draw this picture. I will have pictures on that, of course, in a minute, but at that point you get some oscillatory behavior. It's not this way, but you get these kind of bound states in here. You will see pictures in a minute. Okay, so then another feature, another fact of these molecules is that they are very polar. You have the huge distances between the two the neutral core and the ionic core, and the decentering, and so you have a largest and most polar molecules you could achieve. Yeah? And now this was predicted in 2000 and actually very recently detected experimentally. And so the ultra-cold environment, because ultra-cold gases are very dense. If you're a Bose condensate, this has a high density as a gas, and so it's quite ideal to have these systems coming out from these ultra-cold gases. At first glance, it might seem a little difficult because you're going to have these outer minima here, or these many minima in this potential energy curve, and it might seem that it's difficult to prepare these systems because they are the minima at very large distances. And to start from a tightly bound system, it might be difficult to prepare these. So let me, before I start getting into the physics of these systems in more detail, let me explain you a little bit, and this is also in view of the fact that Tillman will give a lot of experimental details, I guess, on these Trilobite systems later in his lectures. Let me explain a little bit what the interaction is of this ground state atom that is exposed to the Rydberg electronic cloud. Now, so we have a neutral atom which is put into this electronic cloud, as it was given here. Yeah? We put it somewhere here. So then what you could first guess, you have a neutron and you have an electron. Now this is electron-neutral interaction, so you might want to put there a polarization interaction. That's not a bad idea to do, but you can make your life easier because you are at quite low energies at which the electron, for the high excitation out there in the Rydberg situation, scatters from the neutral perturber. Yeah? So this is low energy scattering, and we know for short range potentials how low energy scattering behaves. Short range means I do have a high enough power of these 1 over r to the n behavior such that I get a definite behavior for the corresponding scattering phases. Let me go through this in small steps. What you all know is in a radial symmetric scattering problem that the total cross-section of the scattering behaves like this. That means the sigma is equal to, and then you have the sum over all angular momenta. L is the angular momentum from 0 to, and then you have the 2L plus 1 times sine squared delta L, and delta L are the scattering phases. The scattering phases of the radial scattering problem. Now, if you go to low energies, then it turns out that these phases have a characteristic behavior with the momentum of the scattering. Yeah? The momentum is represented by k, the wave vector. And these phases, delta L, they scale with some power of these k. But some positive power of k means that if I go with k towards 0, which is the low energy case, which is the energy goes to 0 case, then this scaling assures that a higher power of k drops faster than a lower power of k. And that means that the delta L's, which belong to higher L, are negligible. And therefore, what remains if I go with k to 0 or energy to 0 is that only L equal to 0 partial waves are important. That means only delta 0 is important, and delta 0 goes with k. Yeah, that's delta 0 goes with k, L equal to 0. It goes with k here, then this k squared goes out with that k squared. Because it's small, the sine squared can be replaced by the delta itself. Delta squared is k squared, then k squared drops out with k squared, and I remain with something which is essentially constant. Now there's a proportionality here, so there's a constant coming, and this constant which comes is the scattering length. So just one more comment. This line of argumentation is fine if you have short-range potentials. Generally, short-range potentials mean that the n of the 1 over r to the n interaction of whatever you have, generally in the scattering, is n larger equal 4. If you have a dipole-dipole like 1 over r to the third, this kind of behavior is not valid. So now we know in the scattering process we have essentially only the delta zero, which plays a major role, and the underlying scattering length is the relevant parameter. Then the scattering cross-section is just 4 pi a squared. A is the scattering length. Then the idea is, which goes back to Fermi, the idea is not to use the true interaction potential between the electron and the neutral perturber, but to replace it simply by a so-called pseudopotential, yeah? By a Fermi-type pseudopotential, which is given here. Or you might call it an effective contact interaction. These are alternative names for this potential. And how does it look like? Well, it's very simple. It's just a prefactor which involves the scattering length, this A, and then there's a delta function. Now this is of course not a proper description of the interaction of the electron with the neutral perturber, but it is justified through the low energy limit, and it is describing correctly, effectively, the description, the interaction of this electron with the neutral perturber. Now, what you have to take into account here is that the A might depend on the energy. So you don't go strictly to the zero energy limit, but you're a little off. Then you should take into account that A depends on energy. That is what people call an effective range approach. Now, as you see here, if energy gets even larger than just a little bit above zero, then you need to take into account higher partial waves, not only the S wave. That can be done by taking, for example, the next relevant one, which is the P wave interaction. These things become a little nastier, and what is given down here is what we're later going to be taking into account, the choice of the contact interactions, which describes quite a broad range of energies. This is the one part which is the delta interaction due to the S-wave scattering, this part with the correct energy dependence of the S-wave scattering length, and the second part is the P-wave interaction. This is kind of more has derivative operators in it, which come from the fact that you have to have a proper choice of the volume and a proper choice of the boundary conditions. Okay, so this is what we use as an interaction for the electron scattering from the neutral perturber. Coming for a second back to this case, that one would maybe also like to describe this through ab initio methods, not only through this modeling. It is indeed not consistently possible to derive this from an ab initio approach, like a quantum chemistry approach. But one sees, if you go to higher and higher excitations in the quantum chemistry approach, you see something like the emergence of structure which is similar to the structure described by these contact interactions. So there is indications that this approach is indeed a reasonable one from the theory side. Okay, now let me come back to the ultra-long range molecules. There is essentially two classes of ultra-long range molecules. I want to do that, maybe there's more, but two classes I want to address. Yeah? The polar ones and the non-polar ones. And these refer to the fact that you have two classes of Rydberg states for atoms. One class is low angular momentum states. Low angular momentum states penetrate into the core. Yeah, the electrons come close to the core and they scatter from the core. This makes shifts in the energy. So these states are energetically well isolated from other states which have high angular momentum. High angular momentum states refer to the polar case. So if we focus for a minute on non-polar states, which is low angular momentum, something like L equal to 0, 1, or 2, then these have core scattering effects, and what finally quantum defects. This is the energetical shift due to the core scattering. And then if you take these interactions, and just we'll explain in more detail later, take these interactions, then you get shallow oscillatory von Oppenheimer potential energy curves. This is what I've been indicating here, and which is now given here from the work of Hossein and Chris Green and Dickinson. So this is how it looks like. You see that there's oscillations as a function of the internuclear distance, and that there are many local welts and minima, and finally the outermost well is the deepest one, and there are several vibrationally bound states in this outer well. And if you do a small calculation, which actually is easily done in this case, then you see that the U of R, which corresponds to my epsilon of R over here, that the U of R, the potential energy curve, is simply given by the wave function itself. So that means these oscillations are here do come from the oscillations of the Rydberg electronic wave function. In this case of the splitted, quantum defect splitted states, they come very directly. And then there's an R dependence due to this effective range, additionally. Now there's a second class. These are polar states. Now these are the states which emerge if you couple many high angular momentum states. Yeah? Like, think about the hydrogen. Hydrogen, everything is degenerate. And all states for a fixed n are degenerate with respect to L and to M. The orbital angular momentum and the magnetic quantum number. Now, if you go to states, if systems like rubidium, where you have low angular momentum states being splitted off from the degenerate manifold, then still the high angular momentum states of Rydberg atoms are degenerate. Now, if you put that perturber into such a cloud, it couples all these degenerate states, yeah? And it mixes them. And as it turns out, again, a result from this work, what happens is that you get a potential energy curve which couples all these states, and this nodal structure, which you see also here, comes from these radial wave functions of the hydrogenic case. Yeah? So this is the R and Ls which you're used to from hydrogen, and they now depend on the you have the dependence on these R, which is the position of the perturber. The capital R is the position of the perturber with respect to the positively charged core, the internuclear distance. Yeah? And this internuclear distance defines then, this L and L of R defines then how these potential energy curves look like. And again, similar to this case, we have oscillations, but additionally on top of that we have an overall envelope behavior which is for low energies, which is giving an additional global minimum in the system. Okay, so these high angular momentum states are deeply bound, higher binding energies, and they have in particular large permanent electric dipole moment, which is of kind of that size, which is this order of R. This is how these so-called trilobite states, the states living here are trilobite states. This is how they look like. This is where the perturber is, yeah? And this is how the overall electronic wave function looks like. Reminiscent of this ancient animal, which is actually kind of has the same similar shape like this wave function profile. Now, a few more comments before I step on to what I really want to explain to you in terms of dependence on external fields. These systems, similar to the Rydberg atoms, have quite long lifetimes, and so ranging from hundreds of microseconds to hundreds of milliseconds, depending whether they are non-polar or polar. Then p-wave interaction creates additional states. These additional states are so-called butterfly states, and they emerge again from these degenerate high L states, and they have quite a different appearance, might remind you, as the name says, of butterflies. Now, a very short summary of recent developments. These features, which have been predicted in 2000, have been detected experimentally in a spectacular experiment by Tilman Pfau. I think he will be reporting on that. So they have been experimentally, which push the whole field. Beyond that, there have been Rydberg trimers detected and also explained theoretically. And Jan Michael Rost has been the key theoretician. And then this was in 2010. And then the non-polar species, there has been a work which with Hossein and the Dresden group about permanent electric dipole moments in non-polar systems, in homonuclear systems. Now, I'm coming to the point which is the central part of this lecture, the impact of external fields on these ultra-long-range molecules. So it's obvious these are very weakly bound, so the external fields should have a strong impact. The perspective here, generally for me, is somehow you can place a neutral perturber in there, which is a neutral ground state atom, but in principle the pathway is open to put more complex systems or several perturbers into these electronic wave functions and create all kinds of exotic species. But here we will focus on putting a single neutral perturber, atomic perturber, into the Rydberg cloud. First step, switch on an electric field and see what happens. Second step, creating giant dipole molecules in combined fields. So, the static electric field case. So what do we have over here? We have a kinetic energy, if you talk about the Hamiltonian, a kinetic energy, of course, for the relative motion of the ionic core and the neutral perturber. That is sort of the vibration of the system. Then you have the electronic Hamiltonian, which is the Rydberg electron, which interacts, of course, with the ionic core and which interacts with the perturber. This is given in here. So the electron, here the electronic Hamiltonian is H0. This is the kinetic energy of the electron. This is the scattering of the electron from the ionic core, which of course has a structure. It's not only a charge, it's many electrons. Like a rubidium, it's n-1. If rubidium is n electrons, it's one less. So you have what's called a pseudopotential, how you describe this over here. Yeah? You don't need to worry about this structure. That is something which you know from theory. Yeah? So that is the electronic Hamiltonian, and it has this electric field term in it. Now you have also in the total Hamiltonian, of course, the interaction of the electron with the neutral perturber. This is this VNE, neutral electron. And this is given here, and you know it. I've been trying to explain to you. This has this pseudopotential in it, the S wave part and the P wave part. And then you need to fix the energy, you need to fix the wave vector of the electron at which it is colliding with the neutral perturber, and this is given here by this simple relation, which just refers to the fact that you have kind of the electron being with a kinetic energy k squared over 2 and being somewhere at a distance from the ionic core according to the position of the neutral perturber. Okay, and then what you do is you have an eigenvalue problem. You do upon Oppenheimer approximation. That means you separate the fast electronic from the slow internuclear motion, the vibration. So you have an electronic wave function, a vibrational state wave function, and you get an energy surface. And that energy surface you get by solving the electronic Schrödinger equation here. Yeah? Now, how do you solve that? Well, you make a basis set superposition, and you diagonalize the corresponding Hamiltonian matrix. Yeah, and then you get out of that, as a function of the internuclear distance, this potential energy surface, which you're seeking for. And you do that for the high L states. We focus on the high L states over here, typical values for n, something like 35 or 40. And then there are some symmetry properties which you can easily derive for the potential energy. Now, a comment left over P wave, the P wave interaction, this part over here, is a bit of problematic for short distances. It has a resonance. Yeah? That is resonance leads to a regime where the P wave interaction dominates the whole potential energy surface. You have to take care of that and see whether this singularity causes any problems. Now let's have a look into the electric field case. What I'm showing you over here is as a function of r and of theta, the potential energy surface. Now why theta? The problem is that if you have an electric field, and if you have additionally a neutral perturber, then there is a dependence of the energy on the angle between the two. That means if you have here the electric field, and if you have here the monocoque, the internuclear axis, then this angle theta is a relevant angle in terms of the fact that the energy of your system depends on this angle. So truly you have two-dimensional surfaces for the energy, potential energy surfaces. This makes a difference to the normal case without field, because without field what you have is only a dependence of the energy on the internuclear distance. Now it's a two-dimensional potential energy surface. And these two pictures show you color plots for this potential energy surface for two different values of the electric fields. The one is 150 volts per meter, and the other one 300 volts per meter. And what you can see, first, this is blue is low energies and red is high energies. What you see is that you get this kind of oscillatory behavior, deep blue, lighter blue, deep blue, along this radial coordinate, but then at the same time a strong confinement of the angular motion to theta equal to pi, which is the anti-orientation with respect to the electric field. So the system tries to anti-orient, but then it has also angular motion. So, and the confinement gets stronger if you go from the weaker to the stronger electric field. So, in essence, you turn a rotational degree of freedom, namely this angle over here, you turn it to a vibrational one. You have certain equilibria, and if you increase E, you increase, you get a stronger confinement of the angular motion, and in that I will come back to you in a minute, you have stabilization of the S-wave dominated molecular states. Let's have a look at this in a little more detail. Now, there's one issue which you should note. I told you there's the butterfly states and that there is the Trilobite states. The Trilobite states have a different behavior in terms